In today's video, we're going to look at the real number system. So underneath the real number system, the first two syllabus objectives involve binary operations. So the first one, 2.1, states that we should know how to perform binary operations, and the second involves concepts relating to binary operations, and then we need to learn how to apply them. But before, I wanted you guys to learn some math symbols, of course. The first few involve sets of numbers. So it's important that we learn this, especially for this topic, but not only, okay? All of these here are very important to just learn throughout your pure math life and your entire math life, actually. I'm sure you're very familiar with some like therefore and if and such that, but these might be new. Well, not there exists, but for every and for all. You'll see the applications, but for right now, I want you to pause the video, write down all, and memorize each and every one of them. Okay, now getting into understanding the topic of binary operations, we need to learn the sets of numbers. So we're going to focus on real numbers, okay? So real numbers, there are different types, different subsets of real numbers. There's irrational, rational, integers, whole numbers, and natural numbers. As you can see, I put the symbols next to each because it's important that we know them. So we'll start with irrational numbers. They are real numbers which cannot be expressed as a ratio of two integers. So for an example would be the square root of 8, the square root of 11, pi, things like that. Then the opposite of irrational numbers are rational numbers, of course, symbol being q. And these are any number that can be expressed as a ratio of two integers, okay? Then they are integers, so the symbol is z, and these consist of all whole numbers and negative natural numbers. So I put a little example here, and it goes all the way and all the way on each side. So there's z positive, which this is a symbol. These two symbols you also need to know, and all this means is the set of positive integers, and z negative is set of negative integers. Right. Now we look at whole numbers, and this includes all natural numbers and 0, and the natural numbers are these, which are called counting numbers, which include all of these all the way to positive infinity, okay? So basically, this goes all the way hundreds and thousands, millions, whatever. Okay, and the whole numbers includes these natural numbers and a 0. So I put it into a diagram here. Hopefully it could help you understand them better, that they're all kind of related in a sense, they're like a family. But yes, speaking of that, let's actually get into the topic itself, understanding a binary operation. Before we go into binary operations, so I want you to understand what a unary operation is. So a unary operation is an operation that has only one input, okay? And we all know that bi means 2, right? So binary would have 2 inputs. Unary is 1, okay? So the operation is performed on a single element, unary. Some examples would be the square root, the sine of a number, cosine, things like that. So all of these operations only involve one number. Then we can look at binary on the other hand, which is what we'll be focusing on. And we know that addition, subtraction, multiplication, division, we need to have 2 numbers to be able to complete the operation. So an example here would be 11 by 11 is 121. We needed 2 numbers to be able to complete the operation, and that's why it's called a binary operation. And these can be represented by a bunch of different symbols. These are just some examples here. Right, so now we're going to go on to the first property, which is called closure. If we operate on 2 elements of a set, I want you guys to listen to me carefully. If we operate on 2 elements of a set and end up with an element of that set, then that set is closed with respect to the operation. Okay, so now this is the more technical term that I've kind of tried to make simple by giving little, it's not really explanations, but you'll see. So this is the more technical term. For a binary operation, star, if A, B are elements of A, which is a set, okay, so we could put like real numbers, and A star B are elements of A, meaning the operation. So you have the two variables here, and these are two numbers, okay, and you do the operation, and they're still the same set that these two numbers were from. So you operated on these two elements, and they're still in the set of, let's say, real numbers. We said real numbers, right? Then A, real numbers, is closed with respect to that operation. Okay, if you got confused, don't worry, we're gonna break it down just now with an example. So this is just a symbol for an operation. Remember, I told you it could be any of these here and more. Okay, so that don't get scared with the star. Then if A, B, these are just placements for numbers, okay? A, this capital A, is a placeholder for a set, so it could be integers, real numbers, anything like that, okay? Then this set is closed, and remember this is with respect to the operation, whatever the operation may be. So let's look at an example to understand it better. A binary operation, and another symbol as you say, is defined on the set of real numbers R. Remember, we learned about real numbers before, so you should know about that. As A cross B is equal to 2A plus 3B. This is just a bunch of substitution, right? And we'll get into that after. But for prove that, we have to prove that this is closed in R. Remember, it says for all A, B in R. Okay, so we know that these are real numbers. And then we have to say that by stating this, right? So A, B are elements of real numbers. So this is the set here, right? So we know that multiplication, if you multiply 2 by A, it will still be a real number. And if you multiply 3 by B, remember this is the operation going on here, right? So it's 2A plus 3B. So 2 by A would still be a real number. So let's just say A was like 1, 5, 10. Okay, because remember, A could be any real number. It would still be a real number because it's just being multiplied by it. 3B, since B is also a real number, it would still be a real number if it was multiplied by 3. Okay? And that's how we get 2A plus 3B are elements of R. Okay? And let's see. That's how we get to the conclusion that this operation is closed in R, meaning that even after the operation is complete, we know that the answer would still be an element of the set of real numbers. Okay, that's all it really meant. We'll get down to past papers after. If you didn't understand, I'll try to explain it better later. So the next one we're going to look at is commutativity. So the binary operation star is commutative if and only if A star B is equal to B star A. So all that means is regardless of the order of operation, the result means the same. So the order does not matter. So for example would be multiplication and addition, right? So if we multiply 11 by 7, we'd get 77. But if we switched around 11 and 7, put 7 by 11, we'd still get the same result, 77. The same goes for addition. 11 plus 7 is 18, and 7 plus 11 is 18. However, if we were to use it with subtraction and division, we'd realize that they're not commutative, because if we switch these elements around and say, okay, 11 minus 7 is 4, then we try to switch it around. 7 minus 11 is not 4, is minus 4. So subtraction is not commutative. And the same thing goes for division in this example. So let's look at this question. Now looking at this question, the binary operation star is defined on the real numbers as follows. A star B is equal to A plus B minus AB, where A and B are real numbers, right? So we need to show that this operation is commutative. So in your exam, you will have to state that this is what you have to find. So you have to say that star, the operation, is commutative if A star B is equal to B star A, meaning the order does not matter. Okay? So we were given A star B already. All we need to do is find B star A, and we simply do that by substituting B into A and A into B because of their positions, right? So it would be B plus A minus BA, and then we can easily switch around these because it doesn't matter if we switch these around. Remember, addition and then multiplication is also commutative, so it doesn't matter if we switch these around. And you notice that they are equal, and that means that it is commutative. Since A star B is equal to B star A, star is commutative. Great. So in exams, you might be presented with a table of values, and they might ask you to prove if the operation is commutative. And there's two ways we can do this using the table. The first way is we can test the values, and the second way is we can look for symmetry along the leading diagonal. So the first way we're going to look at is testing values. So to do that, we have to look at, we can choose any random values. Obviously we can't choose 1 star 1 or 2 star 2 because you can't just switch around the numbers. It'll be the same. So we have to choose two different numbers. So let's start with 1 and 1 star 4. So 1 star 4, the common number here is 1. Remember 1 and 4. Now we have to switch around the numbers and put 4 and 1. You see, now we have 1 and 1. So those are the same. So let's test it for something else. 3 and 2. Okay? So 3 and 2. We have 4. Now we have to look for 2, 3, 4. Right? So because these numbers are the same, it's commutative. So the second way we can look at it, look for commutativity, is a line of symmetry. All we have to do is draw a diagonal line across these numbers here, and you look for if the numbers on opposite sides are the same, which it is. Okay, 1, 1, 2, 2, 3, 3. They are the same. So that means that it is commutative. Great. Now we are going to look at associativity. So all this is saying is regardless of the way in which the elements are grouped, the outcome remains the same. And we're going to have to test this, right? So they might ask us to prove it and or determine whether or not it is associative. So we're going to look at a question to be able to see how to do it. So the question states, the binary operation triangle is given by A triangle B is equal to AB plus 1. Determine whether or not the operation is associative. So to solve this, we have to first state what we're going to look for. So you have to know the rule. Okay, this is what we're going to look for. And then we are going to separate it into left-hand side and right-hand side. And for it to be associative, we know that the left-hand side and right-hand side must be equal to each other. So first we'll do the left-hand side, which is this. Okay? But to do this, we have to start with one side at a time, and we're going to start with the brackets first. Right? So we're going to treat B triangle C as B in the operation and do a simple substitution to then get the final. Of course we have to simplify, you guys know how to do that, and then get ABC plus A plus 1. So now we have to do the same thing on the right hand side, and we're going to treat this as A star C, triangle C, sorry, and then continue here. And then you can see we conclude ABC plus C plus 1, which is not equal to the left hand side, and therefore it is not associative. And you have to write your statement at the end that it is not, and why. Distributivity. So this states that for any two operations, star and triangle, star will distribute over triangle if and only if, and then we state the rule. So yes, it is the most complicated looking one, but we'll look at an example to understand. It's actually really simple because in this one I use actual numbers and we get a proper value. So the example states that two binary operations are defined over the set of integers such that x star y is equal to xy plus 2 and x triangle y is equal to x over y is star distributive over triangle. So the solution states, well, of course, we must say what we need to look for. So this will be the left hand side and this will be the right hand side, and we find them separately, and if at the end they are equal, then we know that it is distributive, associative, whatever, right? So we say, first of all, I'm gonna let these equal values. These can be any values you like. So I like to keep it simple, of course. So I let x equal to 1, y is equal to 2, and z is equal to 3. So we start with the left hand side and we say, okay, this is the left hand side, and we start. Remember, the operations are defined up here. So y triangle z would be y over z. Remember, basic substitutions, and we simplify. So after I get all the operations solved, I just substitute the values that I created up here and I get 8 over 3. I do the exact same thing for the right hand side, making sure to complete the brackets first, then using the brackets in this operation, the triangle operation here, and getting a conclusion after substituting my values as 4 over 5, which we know is not equal to 8 over 3. So we have our concluding statement. Since the left hand side is not equal to the right hand side, star does not distribute over triangle. So it's that simple. All you need to know is all you need to do is memorize the rules, okay? And know your substitutions. Try not to get mixed up with the substitutions. I know it could get super confusing sometimes, seeing the same letters over and over. Identity. So any element operated on the identity element is the element itself, okay? But before we go into me explaining it for addition and multiplication, I want you to note that the operation must be commutative for the identity element to exist. So you know that addition and multiplication are commutative, and that's why the identity element exists for these two operations. So we're going to look at addition first. For any real number x, x plus 0 is equal to 0 plus x, meaning that the element itself comes back, because if you add 0 to any number, it is that element. So 1 plus 0 is going to be 1. 100 plus 0 is going to be 100, right? And that's why 0 is the identity element for addition of real numbers, okay? So all I'm saying is that you get back the element after being operated on, right? So the operation was addition and you got back the same x after adding 0, and that's why 0 is the identity element. So for multiplication, it's very similar, but we know that we have to, in order to get back the element itself, we multiply it by 1. And that's why 1 is the identity element for multiplication. So x times 1 will be x, and 1 times x will also be x. And that is why 1 is the identity element for multiplication of real numbers. Remember that since division and subtraction are not commutative, they will not have identity elements. But the general rule is that if there exists an element, e, and it's an element of a set of numbers such that e star, remember, e is the identity element here, and a is just a number, and you get back the number, meaning is equal to this commutative, then e is the identity element, okay? So next, moving on, the final thing we're going to look at is inverse. All this means is that an element operated on its inverse will give the identity element, which is what we looked at before. So we have a little rule here, and this means this. So I don't want you to get confused by reading this entire thing, because all it's saying is that an element operating on its inverse will give the identity element. So there are a few things that we need to note. So the first one is the operation must be commutative for the inverse to exist, just like the one before with the identity. An element operated on its inverse is the identity. Any element which is its own inverse is called a self-inverse, and the multiplicative inverse of 0 does not exist. Okay, so we're going to look at this example, and it states to find the inverse with respect to multiplication of any number x, which is an element of the set of real numbers. So what we're going to do is let y be the inverse of x, and we're stating that y is an element of the real numbers just as is x. Alright, so since an element operated on its inverse is the identity, remember this rule here, this is why it's important to understand the rules here. We say that since an element operated on its inverse is the identity, then x, then we remember we stated that y is the inverse, by y is equal to 1. And remember, we're saying it's equal to 1 because it's the identity. Remember, it is the identity. And why 1? Because we know that the identity element for multiplication is 1. So now all we have to do is transpose for y, make y the subject, and we will have our answer. This will be the inverse. So we can come to the conclusion that every element which x is a real number has an inverse of 1 over x, which will also be a real number unless x is equal to 0. So yes, that is all for our properties and understanding binary operations, and now we're gonna move into past. So now we're gonna do some past papers. The first one we're gonna do is 2017. It states that an operation star is defined on the set 1, 2, 3, 4 as shown in the following table. The first question wants us to prove that the operation is commutative. And remember, there are two ways in which we can do that. The first one is to test values, and the second one is to use our line of symmetry. Honestly, the easiest way is to just do our line of symmetry, the leading diagonal, and check to see if these numbers are the same. And yes, it looks as though all the numbers on the opposite sides are the same, hence the line of symmetry, and that means that it is commutative. However, if you did want to just prove it by testing your values, you could choose random values. So you could say, okay, 2 star 1 is equal to 4, and 1 star 2 is equal to 4 as well, so on and so forth. Okay, so that's how you can prove if it is commutative. Prove that it is commutative. So show that the identity element of the operation is 3. So it is telling us that it is 3. They want us to show it. So we know that by our rule, if 3 is the identity element, then every element when operated on and with 3 will give back the same element, right? So 1 by 3 should give back 1, right? So 1 operated 1 star 3 will give back 1. 2 star 3 should give back 2. 3 star 3 should give back 3. And that's how it works. So 1 star 3 is equal to 1. You see, it gives back the same element, and that's why it is the identity element. Sorry. So 2 star 3 is equal to 2, 3 star 3 is equal to 3, and that's pretty much the point. So yeah. 2018. A binary operation is defined on the set of real numbers R, and then they give us this, and then they ask us for 5. Let's just call that cross for now. Okay, so calculate A cross B is equal to 2A plus 3B, and we know that A will be equal to 5 and B will be equal to 2, so we do our substitution. So it will be 2 by 5 plus 3 by 2, and that's equal to 16. So that was easy. Prove that it is closed in R. So, right, so we know that A and B are real numbers. So because of that, we will know that 2 multiplied by the real number A would be real. Same goes for 3B would be real. And hence 2A plus 3B would be elements of the real number as well. So hence, and then you say the cross or the operation is closed in R, the real numbers. Determine whether it is commutative. So we know as a rule, we have to write down that it is commutative if and only if A cross B is equal to B cross A. Okay, so A cross B is 2A plus 3B. That's given. Now we need to find B cross A. So B cross A is equal to, that would be 2B plus 3A. And we already know that's not equal. So not equal. Since A cross B is not equal to B cross A, then the operation is not commutative. You have to write this entire statement out to get your marks. Right. A binary operation is defined in a set of rational numbers by A star B is equal to A, B on 2. Rational numbers. You guys should remember the symbol for rational numbers is Q. So it's saying that E and B are elements of rational numbers, right? So we want to prove that it is commutative. So for that to be true, A star B must be equal to B star A. And we have A star B already. So B star A is equal to B on 2. And yes, because remember multiplication is commutative, so you could simply switch these two around and get our answer. So since A star B is equal to B star A, the operation is commutative. And we must write that entire thing down. Okay, for two real numbers, x and y, the operation star is given by x star y is equal to x squared plus y squared. Prove that it is closed in R. 2021. Yes. Okay. So we need to prove that the operation is closed. And remember, for it to be closed, these elements must be real as well. So it says that these both are real numbers. So x and y are elements of the real numbers. And that means that x squared would also be a real number, and y squared as well. And hence, x squared plus y squared would be real. And that's why star is closed in R. So it's simple. You basically just have to define these values to be real, And we know that if you square a real number, it is gonna be real as well. Okay, and that's when we come to the conclusion that x squared plus y squared will also be real. And that's how we know that the operation would be closed in R. Remember, write your statements out. Don't just do halfway things like me. Write down your entire statement. So now we want to determine whether the operation is commutative. The operation, well, yes. Okay, so let's just do it. So x star y is equal to x squared plus y squared. So for it to be commutative, x star y must be equal to y star x. So we have x star y already. We need to find y star x. So it would be y squared plus x squared, and that could be rearranged to get the same thing. So yes, since x squared, x star y is equal to y star x, the operation is commutative. So yeah, you just have to write out, I'm just writing out the statement so you see what it would look like. You have to write the entire thing to get your full marks. So yeah, you guys can see it's pretty simple. This topic is straightforward. Just understand the different rules, remember the rules for everything, and you'll be fine.